If you've ever sent a private message or even just typed in a password online, you've used cryptography. It's this invisible shield that protects pretty much everything in our digital lives. So today we're going to crack the code on the secret world of ciphers and secret keys. Think about it. From your banking app to your DMs, we are constantly sending our most sensitive information out into the open. And the only thing stopping prying eyes is this ancient art of secret writing, an art that is now blown up into a super high-stakes digital war of wits. So what are we really talking about? Well, at its heart, cryptography is just that, the science of keeping secrets. It's the toolbox we use to make sure that when we talk to someone, absolutely no one else can understand what we're saying. To really get this, we need a kind of battle plan. First, we'll look at the fundamental problem of keeping secrets in the first place. Then, we'll see the first weapon in this war, the simple substitution cipher, and of course, how codebreakers fought back. We'll watch the arms race escalate to stronger ciphers, we'll explore a theoretically unbreakable code, and finally, we'll uncover the key principles that shape all modern security today. So what is the core challenge here? Well, imagine you need to pass a secret note in a crowded room where literally anyone could grab it and read it. That's the internet. And that's the fundamental problem that cryptography has to solve every single second. Let's make this a little more personal. In the world of cryptography, we use a few classic characters. This is Alice. She wants to send a private message to her friend Bob. But there's an eavesdropper, let's call her Eve, and she is always listening. So Alice needs a way to scramble her message so that even if Eve gets her hands on it, it's just meaningless gibberish to her. And the process is actually pretty straightforward. Alice takes her original message, we call that the plain text, and she uses a secret key to encrypt it. That turns it into a scrambled message, or ciphertext. Then, Bob uses the exact same key to decrypt it, turning it right back into readable plain text. The key you see is the one piece of information that Eve absolutely cannot know. Okay, so let's arm Alice with her first weapon. One of the oldest and simplest methods out there is the substitution cipher. The idea is really simple. You just replace every letter with a different letter, according to some fixed system. A really famous example is the Caesar cipher. They say Julius Caesar himself actually used it. In this case, the key is just a number. Let's say we pick 4. You take each letter of your message and you just shift it forward 4 places in the alphabet. So A becomes E, B becomes F, C becomes G, and you get the idea. So if Alice's plaintext is I am Alice, using our shift of 4, it becomes E we weya. Now, to our eavesdropper Eve, this is just nonsense. But Bob, who knows the secret key is 4, he just shifts every letter back by 4 to read the original message. Simple, right? Maybe a little too simple? Because for every codemaker, you can bet there's a codebreaker. And these simple ciphers, well, they have some really glaring weaknesses that someone like Eve can totally exploit. And the science of breaking codes, that's called cryptanalysis. So Eve basically has 2 main ways to attack this. The first is just brute force. I mean, with only 26 possible shifts, a computer can try every single one in microseconds. It's trivial. But there's an even cleverer attack. It's called frequency analysis. See, every language has a kind of fingerprint. In English, the letter E is the most common, by far, followed by T, then A. A simple substitution cipher scrambles the letters, sure, but it preserves this fingerprint. So if Eve looks at the coded message and notices that W is the most common letter, she can make a pretty good guess that W actually stands for E. With just a few clues like that, the whole message starts to unravel. Okay, so the simple shift cipher is broken. Alice needs a better weapon. The codemaker's response was to escalate the arms race by making the key, and therefore the challenge for the codebreaker, exponentially, unbelievably bigger. So, instead of a simple shift, what if the key was a complete random scrambling of the entire alphabet? A maps to Q, B maps to X, C to P, and so on for every letter. This is what we call a permutation-based cipher. Now, frequency analysis might still give you some clues, but trying to brute force every possible key, that becomes a truly astronomical problem. Just how big a problem are we talking? The number of ways you can scramble 26 letters is 26 factorial. That's a number with 27 digits. It's over 400 times septillion. That number is so ridiculously large that all the computers on Earth working together could not crack it in the entire lifetime of the universe. The arms race has officially gone nuclear. This arms race eventually led to a really fascinating concept, a cipher that is mathematically proven to be unbreakable. It's called the one-time pad, and it pretty much represents the absolute pinnacle of theoretical security. The magic behind it is all in how it combines the message with the key. You can think of it like this special kind of mathematical mixing. You take your message, you mix it with a completely random key, and you get the ciphertext. But here's the incredible part. If you mix that ciphertext with the exact same key a second time, you get your original message back perfectly. And this example right here brilliantly shows why it's unbreakable. We have a piece of ciphertext. If you try to decrypt it with one possible key, you get the message, Heil Hitler. But if you use another, equally valid key, you get Kill Hitler. The point is, without the correct key, every single possible plaintext message of the same length is an equally likely decryption. The ciphertext gives an attacker zero information. It is perfectly, provably secure. So if it's perfect, why don't we use it for everything? Well, there's a catch. The rules are almost impossible to follow in the real world. The key has to be truly random, it must be just as long as the message, and you can only ever use it once. But the biggest problem of all is sharing that key. I mean, if you already have a totally secure way to send your friend a giant secret key, why not just send the message that way instead? So, while the one-time pad isn't very practical for most things, this whole historical arms race taught us some incredibly important lessons. And these lessons form the foundation of all modern cryptography. And this leads us to what is probably the most important rule in modern security, Kerckhoffs' Principle. It's a little counterintuitive at first. It says a system should be secure even if the enemy knows exactly how it works. The only thing that should be secret is the key. And this is genius because it allows thousands of experts to analyze the system, find flaws, and make it stronger over time, something a secret design could never achieve. Real strength comes from public scrutiny. So what makes those public algorithms strong? It really boils down to two principles, defined by the father of information theory, Claude Shannon. The first is confusion, which just means you want to make the relationship between the key and the final ciphertext as complicated and tangled as possible. And the second is diffusion, which means that if you change just one single letter in your original message, it should completely change about half the letters in the ciphertext, hiding any patterns. Modern ciphers are built by just applying layers and layers and layers of these two ideas. Which brings us all the way back to this fascinating paradox. In a world where all the best locks and security systems have their blueprints available online for anyone to see, how can anything possibly stay secure? It turns out the entire strength of our digital world doesn't rest on secret methods. It rests on the simple yet incredibly powerful idea of a secret key.